Hello, everyone, and welcome to Lecture 13 on Solutions and Colloids. Just to recap a little bit about matter, if you recall, matter is composed of one, pure substances, which can be elements or compounds, and two, mixtures, which are categorized as homogeneous or heterogeneous. A solution is a homogeneous mixture of two or more substances. Each substance in the solution retains its own chemical identity. The solvent is one of those two components in a solution, and it is the component that is in excess. The solute is the component that is dissolved in the solvent. A solution can contain two or more components, one solvent, and one or more solutes is what is contained in a solution. Can have variable composition. If you remember when we talked about elements and compounds, they have fixed composition by mass. But a solution can have a variable composition because it can have certain volumes of solute and certain volumes of solvent, or certain masses of solute and certain volumes of solvent. And the ratios of those two species can be varied. If you change the ratio of the solute and the solvent, you also change the properties of the solution. In terms of homogeneity, solutions have uniform properties throughout. The particles that are associated with solutes are dissolved and they intermingle as individual particles within the solution. What are those particles? They are molecules, atoms, or ions. Solutes do not settle out of solution over time, but they can be separated by physical means. The definition of solubility is the maximum amount of solute that will dissolve in a given amount of solvent under a given set of conditions. There are several factors that affect solubility: solvent properties, temperature, pressure, and the presence of other solutes, and we'll talk about each of those independently. The solubility of a solid in water or another solvent increases with increasing temperature. However, the solubility of a gas in water decreases with increasing temperature. That's why when we have soda, for example, we put it in the refrigerator, because keeping it cooler keeps the gas dissolved in the solution. There are limited effects of solubility of solids and liquids in water associated with pressure, because if you think about a solid or a liquid, the particles are very close together, they're closely packed. And so there isn't a lot of space for those particles to be compressed by pressure. Gases, on the other hand, are affected by pressure in a huge way because the particles of a gas are very far apart. William Henry, or Henry's law, shows that pressure above a gas increases into a liquid solvent with increased pressure. And the opposite is also true. If you have a gas above a liquid and you decrease the pressure, the gas will be less soluble in the liquid. There are three ways that we can qualitatively categorize solutions. The first is an unsaturated solution. In an unsaturated solution, we have less solute dissolved relative to a saturated solution. And you can see over here in the little diagram that we could potentially dissolve more solute particles if we wanted to. A saturated solution has the maximum amount of solute dissolved in it. A saturated solution is assumed to be at equilibrium, which means that there are equal amounts of solute dissolving and leaving solution. In a saturated solution, if we add more particles, you can see that the dissolution process is not occurring. A supersaturated solution is very unstable because we have more solute temporarily dissolved than we would with a saturated solution. How do we possibly get more solute dissolved than we would have with a saturated solution when we've already seen that a saturated solution has no dissolution process going on once you surpass saturation? Well, we heat the solution up, and when we heat it up, we can get more solute into the solution, and because it's very unstable, we have to cool it down very, very slowly. Here are 3 panels, A, B, and C, in a figure showing you what happens with a supersaturated solution when that stability is pushed in one direction or the other. So in panel A, you can see a saturated solution where we have more solute than would be dissolved in a saturated solution, so it becomes super saturated. But you can see that there are a pair of forceps here, and that pair of forceps is dropping into this supersaturated solution one more little crystal of solute. When that one more little crystal of solute drops into that very unstable supersaturated solution, you can see in panel B that all of the solute starts to drop out of the solution. And by the time we get to panel C, you can see that almost all of the solute has dropped out of that solution. This slide is showing you the lack of stability in a supersaturated solution. Qualitatively, we can also designate solutions as being concentrated or dilute and aqueous or non-aqueous. A concentrated solution contains a large amount of solute relative to the maximum dissolvable amount. And so the question might be, well, aren't we just talking about a supersaturated solution? But we're not, because a supersaturated solution contains more solute relative to the maximum dissolvable amount, where a concentrated solution contains a large amount of solute that's relative to the maximum dissolvable amount. In a dilute solution, we have a small amount of solute relative to the maximum dissolvable amount. And this is very similar to an unsaturated solution. So often people will use dilute solution or unsaturated solution, both having the same meaning. An aqueous solution has the solvent water, and a non-aqueous solution does not have water as the solvent. And so a non-aqueous solution may have something like toluene or a hexane or ether as the solvent. We're showing a concentrated versus a dilute solution here because these two terms are often used with acids and bases more than any other solution. Acids and bases are very corrosive, and depending upon the concentration, the burns that they cause to human tissue can be much, much worse. You can see on the left in that panel, we have sulfuric acid concentrate, and you see that it says CONC dot. So that's conc, and we call that's a short abbreviation for concentrate. Concentrate sulfuric acid or other concentrated strong acids have very strenuous vapors. And so you can see the vapors that are coming up out of that beaker and out of the bottle that's holding that concentrated sulfuric acid as it's being poured. Those vapors are toxic. They're corrosive to the respiratory system. If you inhale them, they'll burn. If they get in your eyes, they will burn. They can cause such burns if they concentrate into a certain spot in the eye that they can cause blindness. You can see on the right side, we have sulfuric acid dilute, and that's abbreviated with DIL dot. So when we open up a bottle of dilute sulfuric acid, we're not going to get all of those vapors and fumes coming out. that are going to burn your lungs and your respiratory system if you inhale them. So it's important that we have chemical species that are so corrosive labeled as concentrated or dilute. There are certain solubility rules, and the main rule that we're going to focus on in this class is like dissolves like, which means that polar substances tend to dissolve in other polar substances, which you've already seen when we talked about Vesper. Nonpolar substances tend to dissolve in other nonpolar substances. There are some ionic deviations away from like dissolves like, but those solubility guidelines are not at the level of this course. This brings us to talk about quantitative concentration. So we've talked a lot about qualitative concentration. Let's talk about quantitative concentration that we can get an actual value for. The first type of quantitative concentration we're going to discuss is percent concentration. That is percent by mass, where the units are in grams. And the grams cancel because we have mass of the solute over mass of the solution. The grams cross cancel. We multiply times 100, and so our units are literally percent. The mass of the solution here is equal to the mass of the solute plus the mass of the solvent. We also have percent by volume, where the units are in mils and cancel. So we have volume of the solute over volume of the solution. The units in mils cross cancel, and we're left literally with units of percent. And then we have mass volume percent, where we can have units in grams per 100 mils. So the mass of the solute is in grams, the volume of the solution is in mils, and so those units don't cross cancel. We multiply that times 100, but by convention, we just write that that is a percentage. So we use units of percentage. Molarity is very, very common. Molarity is represented by this uppercase M, and it is sometimes italicized, but the units are moles of solute over liters of solution. So let's look at a calculation for percent by mass. This question says, what is the percent by mass concentration of sucrose in a solution made by dissolving 7.6 grams of sucrose? So we know that we have 7.6 grams, and we know that sucrose is our solute. We're dissolving that in 83.4 grams of water. And so we know that the water is our solvent. We know the formula for this is grams of solute over grams of solution. And we multiply that by 100. And we also know that the grams of solution are equal to the grams of solute plus the grams of solvent. So we can start plugging into this formula. So we have our grams of sucrose, that's our solute. So that's going to be 7.6 grams. And that's going to be over the total grams of the solution, which they give us grams of water, that is the solvent. So we're going to add the solute and the solvent together. So this is 7.6 grams of solute plus the 83.4 grams of solvent. And then we multiply this by 100 to get our final answer. I get 8.351648. I'm going to cut it off there because I know that my sig figs are much less than that. So when I look at my significant figures, I see that I have 7.6, that's two significant figures. And here I have the addition subtraction rule. When I add those two together, 7.6 plus 83.4, I get 91. I know that the addition subtraction rule says that my answer is going to contain the same number of digits to the right of the decimal as my data value with the least number of digits to the right of the decimal, and both of those data values have one digit to the right of the decimal. So this is going to have to be 91.0. 7.6 is two significant figures. 91.0 is three significant figures. Now I'm doing division. Division multiplication rule says that my answer is going to have the same number of significant figures as my data value that has the least number of significant figures. So my answer will have two significant figures, putting me at this 3. I evaluate the next digit over, which is 5 or greater. So my answer is going to be 8.4 as I increase the last retained digit and then drop the rest. And my units, of course, are percent. Here's the solution from the publisher. And let's try another example. This example is asking how many grams of sucrose must be added to 375 grams of water. So I can start taking notes over here on the side. If I need grams of sucrose, that means that I need grams of solute. And then it says I have 375 grams of water. And so the 375 grams of water is my solvent. And I have a solution that is 2.75% by mass sucrose. Okay, so that's all the information that I have from this problem. I also know, though, that I need the mass of the solute over the mass of the solution times 100 to get the percent mass by mass value. And I know that in this problem, my percent mass by mass is equal to 2.75. So I know that in order to get that 2.75%, I had to multiply by 100 because it's a percentage. So I know I had to multiply by 100. And I had to have, or I could have had in a 2.75%, 2.75 grams of solute if I had 100 grams of solution. And the reason that I know this is because I know about math and cross-canceling. And in this problem, the 100s would cross-cancel. And this 2.75 is equal to this 2.75. So what have I done here? I've just used my knowledge of percentages and cross-canceling and the fact that 2.75 equals 2.75 to set up for myself a conversion factor. Now I'm after the solute. That's what I'm interested in. What I have to start with, though, is the solvent. And so I somehow need to be able to cross-cancel solvent and get to solute, which means I need some kind of a conversion factor that gives me a ratio between solvent and solute. And I actually have one. I've just gotten one together because if I use this knowledge that I have right here that I've just drawn out, well, if I have 100 grams of solution, and I know that the solution is the mass of the solute plus the mass of the solvent, then I can subtract my 2.75 grams of solute and get the mass of the solvent. That is 97.25 grams of solvent. Now, is this the only way that a 2.75% mass by mass solution could be made? Well, no, this isn't the only way. It's just the easy way. I mean, if you think about it, we could have had 5.5 grams of solute over 200 grams of solution times 100. And if you do that math, you'll find out that that is a 2.75% by mass solution as well. And we could have had plenty others. I just multiplied the 2.75 times 2 and the 100 times 2. We could multiply each one of those by 10 or 20 or multiply them by 0.5. And they would all give us a 2.75% by mass concentration of our solution. The fact is that I used this one because it's easy to set up and it's easy to get these conversion factors where now I know the mass of my solvent and I know the mass of my solute. I can warn you that if you don't learn how to use percentages like this to set up your own conversion factors, you're going to run into trouble later in the course. There's a lot of students at the beginning of this course, and I tried to warn them not to move the decimal point to the left or to the right when we were looking at conversion factors for the metric system, because I knew we were going to be using dimensional analysis extensively, and I was trying to teach dimensional analysis at the same time that I was trying to teach the metric system conversions. Now, at this point, I'm trying to teach you how to set up your own conversion factors when you have percentages at the same time that I'm teaching you about concentrations and mass by volume percent. So a lot of you will want to do a back calculation, and that's fine. But what I can tell you is you're cheating yourself out of learning this process. That's number one. And number two, 90% of the students who do back calculations on the test get these questions wrong. So that's just my advice. You can take it or leave it. So let's start to solve this problem now that we have our conversion factors that we need. We start with our 375 grams of solvent. If I don't know anything else, I do know in dimensional analysis that I don't want grams of solvent, water. So it's going to go on the bottom. What I'm after is the mass of sucrose, my solute. So I want the mass of sucrose, and I've made myself a conversion factor of the solute to the solvent. My conversion factor says that if I have 2.75 grams of sucrose, then I have 97.25 grams of water. And I got that from here and from here, which is here also. And now all I have to do is cross cancel my grams of water, which is my grams of solvent, and then do the calculation. And I have my mass of solute, or my mass of sucrose. And I get 10.60411 grams of sucrose. And I'm going to stop there because I know that my significant figures are 3 sig figs here. And I have 3 sig figs here. Both of those came out of the problem. So my answer is going to have 3 sig figs, which puts me here. And when I evaluate the next digit over, it's a 0. So that means that I have 10.6 grams of sucrose to add to 375 grams of water to prepare this 2.75 mass percent solution. Here is the total solution with the same answer. So let's look at another problem. This problem says that normal saline solution is used to dissolve drugs for intravenous use, and it is 0.92% mass by volume sodium chloride in water. That means that sodium chloride is our solute, and so I'm going to start taking notes over here. Water is our solvent. I know that the mass by volume percent is 0.92. They want to know how many grams of sodium. So that's our solute. We're after grams of sodium to prepare 35 mils of solution, 35 mils of this normal saline solution. So I'm going to write 35 mils of solution down here. And now I'm going to start evaluating what I have in terms of units. And so I only have the 2 values. Let's think about this from the same aspect, because this is a percentage that we have as we thought about it earlier. We know that mass of solute over mass of solution, and again, the mass of the solution is the sum of the solute and the solvent times 100. In this case, it's mass by volume. So instead of mass of the solution on the bottom, we're going to have a volume of solution. Okay, so let's think about how this would work with 92%. Again, this equals the mass by volume percent. So if this has got to equal 0.92%, we know that we had to multiply by 100 to get a percent. That's how you get percent. You multiply by 100. If the mass of the solute is 0.92 grams, then we know that the volume has to be 100 mils. Why? For the same reason as last time. that 100 is going to cross cancel, and 0.92 equals 0.92. Again, why did I choose to set it up this way? Because it is easy. It's easy. So now I know exactly what my volume is, and I can cross cancel the volume that I have, so I can start the problem. They're asking for 35 mils. I need to get from 35 mils of solution to how much sodium chloride mass do I need to make that? So 35 mils times. If I'm thinking about the conversion factor that I just made, in 100 mils of solution, I just said it's 0.92 grams of sodium chloride, which is my solute. Now I can cross cancel mils of solution. And again, I probably should have clarified that this over here is mils of solution, because you have to have the same thing to cross cancel. And so then all I have to do is the math, and I'll have grams of sodium chloride, which is exactly what I'm after. So I get 0.322 grams of sodium chloride. Now I'll look at my significant figures, and I got this value from my data, so that is 3 sig figs, and this value from my data, and that is 2 sig figs. So my answer, because this is all multiplication and division, is also going to have 2 significant figures. That's here. When I evaluate the next digit over, it's 4 or less. So my answer is 0.32 grams of sodium chloride. And here's the solution. Let's see what answer they got. 0.32 grams of sodium chloride. So let's talk about molarity. Now, the thing with molarity that differs, that makes molarity very common to use in the lab or in other calculations, is that molarity contains moles, and that's our universal unit. So molarity is represented by this uppercase M, and it is moles of solute over liters of solution. Moles of solute over liters of solution. So let's look at a problem. We have 4.35 moles of potassium permanganate, and so that is our moles of solute. Dissolved in enough water to make 750 mils of solution. Okay, now we're going to analyze our units. That's our next step. And so we have moles of solute. That's fine because that's what we need for molarity. But we have mils of solution, and we need liters of solution. So in order to get liters of solution, we're going to have to do a conversion. I know that I don't want mils of solution, so I'm going to put on the bottom, and I'm going to put liters of solution on the top. I put a 1 by the prefix, and 1 times 10 to the minus 3 is the power of 10 for milli. Then I do the math and I get 0.75 liters. Now, the reason that I'm not carrying this other 0 with me is because when I look at this value, it has 2 sig figs. And so I don't want to carry that extra 0 because when I add the decimal, carrying that extra 0 would make it look as though I have 3 sig figs. And so in this case, where I've told you carry all the digits, in this case, if you do carry that digit, which you can, but if you do carry that digit, you need to make sure that you underline your significant figures here so that you remember that 5 is where your significant figures are. So now I'm going to go ahead and finish this problem. And I have 4.35 moles of solute over now 0.750 liters of solution. And again, I'm just going to make sure that I'm following where my significant figures are. So I have 3 sig figs here, but I have 2 sig figs here. This is multiplication division rule. So when I get my answer, it's going to have 2 significant figures. So I get 5.80 moles per liter, but I know that it has to be 5.8. So my molarity is 5.8. Let's look at another problem for molarity. We have 20.0 grams of sodium hydroxide dissolved in enough water to make 1.50 liters of solution. So the hardest part sometimes is solving these problems, just making sure you know what you have. So if I have 20.0 grams of my solute, sodium hydroxide, and I want to make 1.50 liters of solution. And I know that molarity equals moles of solute over liters of solution. And so when I evaluate what I'm starting with, there's a little problem here because I have grams of solute. I need moles of solute. So I'm going to do a conversion of sodium hydroxide from grams to moles. And no, I don't want grams of sodium hydroxide. So I'm going to put it on the bottom. And I can do this calculation off to the side. So I know that sodium is 22.99 atomic mass units. And I know that oxygen is 16.00 atomic mass units. And I know that hydrogen is 1.01 atomic mass units. When I add all of those together, I get 40 atomic mass units, which is also 40 grams per mole. So I'm going to put 40 grams per 1 mole into this problem. And now I know that I've cross-canceled grams of NaOH. I have moles of NaOH, so I can start plugging in to my formula for molarity. All I have to do is get this value. And that is 20 divided by 40, which gives me, of course, 0.5. But I have 3 significant figures in that 20.0 over here. So I have to make sure that I carry those 3 significant figures into my answer. So that means I have to add 2 more zeros to the moles of NaOH. Now I have 0.500 moles in 1.50 liters. Which gives me 0.333, and these threes keep going and going and going. And this is molar, or I could have written moles per liter, either way. But I need to get my significant figures straight here. And so because I have 3 significant figures in both of these values that came out of the question, then my answer's got to have 3 significant figures, putting it here. I evaluate the next digit, but the issue is that I have a trail of 3s that never ends. So I have to say this is 0.334 molar. Or I could have said 0.334 moles per liter. Either one of those answers is fine. Or I could have written out molar. Okay, let's try this one. And it is your turn, but I'm going to help you with this one. So I'll work through it with you. And we start writing down what we have. So they're asking for grams of sucrose. And sucrose is C12H22O11. And that is our solute. They want to know how many grams of sucrose are present in 185 mils of this solution. So we know that our solution volume is 185 mils. Not our solvent volume, because it says 185 mils of a 2.50 molar solution. And the other information we have is that we have and I'm going to write it like this, moles, and moles is not an uppercase, so I'm going to just erase that. I started to write molarity, but I think it would be better to write it in moles per liter for all of you just for now. Okay, when I analyze what I've got, I know that these mils that I have will not work with the liters that I have. So something's got to be done there, and I'm going to choose the one that's easier to convert, and that's the one with the single units. So when I convert this, I put mils of solution on the bottom, so it'll cross cancel. Liters of solution on the top. I put a 1 by the prefix, and 1 times 10 to the minus 3 is the power of 10 for milli. Now my mils will cross cancel. Mils of solution actually cross cancel. And I can do the math, and I get 0.185 liters. Okay, now I know that I'll be able to use this volume of my solution with my concentration of my solution to cross cancel that volume and get to moles of my solute, so I can use molar mass to convert those moles of solute to grams of solute. So I start with my 185 liters of solution. And I'm going to make sure that the liters, and I have 1 liter of solution, that's on the bottom, and the 2.50 moles and again, that's moles of solute, is going on the top. So that is moles of C12, H22, O11, and it's important that you memorize that for cross-canceling per liter of solution. Now, liters will cross-cancel of the solution, but I have moles and I don't want moles. So I'm going to use molar mass. And in 1 mole of C12, H22, O11, how many grams of C12, H22, O11 do I have? That's the question. So I can go off to the side and calculate this. If I have 12.01 times 12 carbons plus 1.01 times 22 hydrogens plus 16.00 times 11 oxygens, what do I end up with? That's 144.12. This is 22.22, and this other one is 176. So when I add those together, I get 342.34. So now I can see that moles of my solute have cross-canceled. I have grams, and that's what they're asking for. So liters of solution cross-cancel, moles of solute cross-cancel. I have grams, and now I just do the math. And I get a pretty big number. Oh, I see why I'm getting too big of a number. I didn't put a decimal here. All right, let's try this again. Yeah, so now I get 158.33225, and that's grams of C12, H22, O11. So now I just need to take care of significant figures. So there are 3 significant figures here. And then we use this value, which is also 3 significant figures. So we need 3 significant figures in our answer, which puts us here. So that would be 158 grams of sucrose. and the publisher gets 159, but the difference is probably the molar mass of sucrose. Okay, so let's look at this problem. A typical dose of iron 2 sulfate used in treatment of iron deficiency anemia is 0.35 grams. So if we start keeping track of what the problem's giving us, then we have 0.35 grams of FeSO4. It's used to treat iron deficiency anemia, and they want to know how many mils of a 0.10 molar solution. So we know we have 0.10 moles per liter of FeSO4 solution. So how many mils would be needed to supply this dosage that we have? Okay, so the one thing that we can see is that we have grams of iron sulfate, and in our concentration, we have moles of iron sulfate. So we're going to need to convert those grams of iron sulfate to moles of iron sulfate. I know I don't want grams, so I'm putting it on the bottom, and I'm going to use molar mass, so that is 1 mole of FeSO4. I calculate off to the side so that I can demonstrate my calculation. And iron, I know, is 55.85 atomic mass units. And then the sulfur is 32.06. I know that there are 4 oxygens, and so that is 16 times 4, which gives me 64, and then I add all of this together. And I get 151.91 atomic mass units, which now is also grams per mole. I cross cancel grams of FeSO4 and I have moles of FeSO4, which is what I need in order to use the molarity in dimensional analysis. So I just do the math. I get 0.002303996 moles of FeSO4. But you see that instead of doing this broken up like that, I could have just kept going. So let's just back up and erase this and put our next conversion factor in here because it'll just be quicker. So I'm going to put 0.10 moles of FeSO4 on the bottom and the 1 liter of solution, FeSO4 solution, on the top. And now I can cross cancel these moles of FeSO4. I'm left with the volume of solution. That's what they're asking me for. How many mils of this solution is needed to supply this dose? So now I just, again, do the calculation and the math. I get 0.023,039. And I can cut it off there because I know about how many significant figures I'm needing. This is, of course, liters. So I need to convert that to mils, and I can do that conversion either by moving the decimal point, or again, instead of stopping there, I could have just kept going, right? So I can get rid of all of this and do my other conversion, putting liters of solution on the bottom and mils of solution on the top. The 1 by the prefix, and 1 times 10 to the minus 3 is the power of 10 for milli. Now I see that I can cross cancel everything. And if I would have been smart, I would have just done this all in one foul swoop. I calculate. And I get 23.03995. Again, this is mils of solution. And now I evaluate my significant figures. I have 2 significant figures here. And the other thing that I took out of the problem are these 2 significant figures here. That's it. So my answer is going to have 2 sig figs, which puts me here. When I evaluate the next digit over, it's 0. So that means I have 23 mils of solution. That brings us to talk about dilutions. Dilutions are pretty important in the laboratory. And the reason that dilutions are really important in the laboratory is because we often, when we're doing experiments, we'll be running the same types of experiments for a year or maybe 2 years or 3 years. And so we might need a lot of the same solution over and over again as we repeat experiments or do multiple trials. And another reason is that a lot of people in the lab might be running different experiments, but they still need to use the same solutions. The only issue is that everybody doing different experiments, they might need the same solutions, but they might need different concentrations of the same solution. We don't want to keep thousands of mils of solution because we don't have the space for it, number one. And number two, we don't know which of those solutions we're going to need and in what quantities. We just know we'll probably need large amounts of quantities. If we make a stock solution that is highly concentrated, then it takes up a lot less space in the refrigerator, and we can dilute it whenever we need a less concentrated solution. So this is done a lot in laboratories where we make highly concentrated stock solutions. They don't take up as much space. And then anyone who needs any concentration that's lower than the highly concentrated stock solution can simply dilute it, and it's very quick. The other reason that we make stock solutions is this: if you need a really, really dilute solution that has a very tiny mass of solute that you're adding to some 250 or 400 or 500 mils of solvent, it's very difficult to get that tiny, tiny mass evenly distributed in that large volume, no matter how much mixing you do. But if you have a stock solution that already has the solute dissolved in it and it's uniform throughout, then it's a lot easier to go from that liquid stock to a very, very dilute solution and have it have the final dilute solution be uniform with solute particles throughout. Now you notice when we're observing these dilutions that on the right side of this particular picture, the solutions look darker than they do on the left side. That's because you have increasing concentration going from the left to the right. And we can observe that if we have the same solute and the same solvent, because again, the more concentrated solutions are going to be darker if we have a colored solution. Dilutions of these stocks, as I told you, are very, very common in the lab. And a defined dilution is the solvent is added to stock to decrease the concentration. And so mathematically, that looks like C1V1 equals C2V2, where this C is the concentration, and this V is volume. C1 is usually the stock, or what we consider to be the initial concentration. It doesn't have to be, but that's typically the way we look at it. And V1 then is going to be the volume of the stock, or that initial solution that we have. C2 is usually the final, or what we would call the desired concentration. So we have a stock, that's C1. What is our desired concentration that we need to dilute to do our experiment? And then V2 is usually the desired volume, and we generally know how much of a particular concentrated solution we need to do our experiment. So we will typically have an idea of 3 out of 4 of these variables at least. And then the other way that we can rewrite this concentration is in terms of molarity. So you'll often see this exact same formula written as M1V1 equals M2V2, where the M is molarity, the V is still volume. But we're just specifying that the concentration now is not grams per mil or grams per liter, it's moles per liter specifically. So let's look at a problem. What is the molarity of a solution prepared by diluting 65 mils of a 0.95 molar solution to a final volume of 135 mils? So if I'm getting confused about what is C1, what is V1, at least I know that my final conditions, my final volume here is this 135 mils. So I can write that down. I can say, okay, V2 I know is 135 mils. So that means that V1 has to be the 65 mils. And that means if V1 is 65 mils, that's 65 mils of a 0.95 molar solution. So that means that M1 has to be the 0.95 moles per liter. And so I'm looking for M2. That is the one variable that I don't have. If I rewrite this C1V1 equals C2V2 as M1V1 equals M2V2 because I'm working with molarity, then I know I'm looking for M2, so I can just divide V2 out of both sides. And that means that V2 over here on the right is canceled. And now I can just start plugging values in to this formula. So I want M1, that is 0.95 molar, times V1, and V1 is 65 mils, over V2, which is 135 mils. And maybe now you can see why I didn't worry too much about the units, because I knew that these mils were going to cross cancel when I divided V2 out of both sides. And I'm left with molarity. I'm looking for M2, so those are the right units. And now I'm just going to calculate the math. And I get 0.457,407, and then it repeats. So I'm just going to leave it at that. And that's molar. And now I need to look at my significant figures. So I got this 0.95 from the question. So that's a data value, and that's 2 sig figs. And I got the 65 from the question. So that's another data value, 2 sig figs. I got the 135 from the question, another data value, 3 sig figs. This is all multiplication and division. So my answer is going to have 2 significant figures. That's here. I evaluate the next digit over. It's 5 or greater. So my last retained digit has to increase by 1. So that's 0.46 molar. Now that leads us to talk about colloidal dispersions. We've talked about solutions. Solutions are homogeneous mixtures where the solute is dissolved in a solvent. With a colloid dispersion, we have particles that are a little bit larger than those of a solution, but the particles are smaller than those of a heterogeneous mixture, and we would consider a heterogeneous mixture that we could compare here to be called a suspension. So a suspension has even larger particles than a colloidal dispersion. The particles of a colloid are dispersed opposed to dissolved. So again, in a solution, the solute is dissolved in the solvent. But in a colloid, the particles are too big to be completely dissolved, so they're dispersed. Instead of a solute, like we have in a solution, we have a dispersed phase. And instead of a solvent, like we have in a solution, we have a dispersing medium for a colloid. So what are some similarities and differences? Because it sounds like we have two different types of mixtures that have some similarities, but we need to know what the differences are so that we can distinguish between them. Well, for both solutions and colloids, the particles are not discernible by the naked eye, so you can't see the particles. And the particles do not settle out of solution, and this is something that I'm going to get back to in a little bit after we go through this. I want to talk to you a little bit more about particles settling out of solution. The particles for both true solutions and colloidal dispersions cannot be filtered out with filter paper, and so we cannot use filtration to distinguish between these two, because we can't filter solutes out of a solution because the particles are too small. They'll go straight through the filter paper pores. And we cannot filter out the dispersed phase from a colloid because the particles are too small still, and they'll go straight through the pores of the filter paper. A suspension can be separated by filtration. So the particles in a suspension or any heterogeneous mixture are large enough that they can be filtered out using filter paper. What are the differences then between a true solution and a colloidal dispersion? The particle size in a true solution is less than 10 to the minus 7 centimeters. And we're talking about ions, atoms, and molecules. This is homogeneous to light, and we'll talk a little bit more about what we mean by homogeneous to light in a minute. The particle size in a colloidal dispersion is 10 to the minus 7 to 10 to the minus 5 centimeters. So a little bit larger. 10 to the minus 5 is slightly larger than 10 to the minus 7, but still, this is fairly similar here. Unless we go over here to the 10 to the minus 5, which seems to have a difference. The difference, though, is large enough to be non-homogeneous to light. And so what do we mean by non-homogeneous to light? That means that if we shine a light on a colloidal dispersion, we'll get light scattering that we don't get when we shine a light in a true solution. This is called a Tyndall effect, because this scientist, Tyndall, is the one who derived the Tyndall test to determine whether you had a true solution or a colloidal dispersion. Remember, we can't tell by looking at them because they both have particles that cannot be discerned by the naked eye. So let's have a look at something microscopic, a sketch of what we can't see with the naked eye. What we have up here is maltose. This is two glucose molecules that are bonded together, and these bonds are covalent bonds. So this is a disaccharide or a molecule of maltose. You put maltose, just like sucrose, into water, and it'll dissolve, and you'll get a solution. Okay, what do we have over here on the other side? This is starch. Starch has a lot of residues of glucose. In fact, if we start counting these residues, you can see that there's one here, there's another one here, there's another one here, there's another one here, there's another one here, and there's another one here. Altogether, that's 6 residues, and so we have 6 residues per turn, and there are 300 to 500 of those residues in a molecule of starch. In fact, this is called in biochemistry a macromolecule. That's what starch is referred to, just like DNA or protein. Those are macromolecules. So this starch molecule is way larger, as you can see, if we have 300 to 500 residues, than sucrose or fructose or maltose, some species that have a molecule that would dissolve in water and form a solution. So starch dissolved, and it doesn't actually dissolve, it's dispersed in water, is going to form a colloid. Again, substantially larger than this maltose solution that we would make is the starch in the starch colloid that we would make. So suppose we had a solution of sugar, like sucrose or fructose or maltose, and we had a solution of starch. Suppose we had some color in the sugar, a little bit of color because it wasn't bleached out like a lot of the sucrose that we see. And so that's what we have in panel A. This is a solution. And you can see when the laser beam is shined on the cuvette holding the solution, it reflects off of the glass, which you can see here, that red reflection on the glass, and you can see a little bit on this side also. But you don't see a red beam going through that solution because that solution is homogeneous to light and it doesn't scatter the light. But when we look at panel B, we have a colloid because we can see right here where the laser beam is reflecting off of the particles in the colloidal dispersion because they're larger, like the starch particles. So panel B is a colloid. And panel A over here is the solution. We have light scattering in panel B, non-homogeneous to light. That's the Tyndall effect. And in panel A, that solution is homogeneous to light. The particles are too small for light to scatter. And which of the following phenomena do not represent the Tyndall effect? So sunbeams are literally light from the sun that is reflecting off of some particles in the air, like clouds, like the particles that are in clouds. The reflection of a flashlight in a pond, you're seeing that reflection because the light is reflecting on the particles that are in the pond. A light reflecting on glass. That sounds like what we just saw in the previous slide, where we had the laser beam reflecting on the sides of the glass cuvette, but we didn't see it reflecting through the solution. So that seems like it might be a good candidate for an answer. Headlights in the fog. Well, that's very similar to sunbeams reflecting off of the clouds. And so that's also a Tyndall effect. So it looks like our best answer is C. Well, let's just back up one slide and talk again about these particle sizes, because we said that this 10 to the minus 7 is very, very similar and makes this true solution look an awful lot like a colloid. But then we have this 10 to the minus 5 that shows some variation. So those folks who are looking at the 10 to the minus 7 are going to say that a colloid is homogeneous. And they're going to say that the particles do not settle out over time. But those folks who are looking at a colloid with particle size of 10 to the minus 5, they're going to say that colloids are heterogeneous. And they're going to say that given long periods of time, the particles will settle out. There's no way to get these two groups of people to agree. And so depending upon the literature that you read or the video that you watch or the handout that you have, sometimes you're going to see the homogeneous argument, sometimes you're going to see the heterogeneous argument. You've got to just know that both of them exist based on the fact that you have this overlap in the size of the particles, and then you have particles that are much larger in a colloid, like starch would be. The only thing that all of these folks agree on is that a suspension is definitely heterogeneous, and with a suspension, the particles will definitely settle out over time. That's the end of the lecture on solutions and colloids. If you have any questions, definitely shoot me an email or bring them to Chem at Night.